Uh, can everyone see my screen?
Yes, your screen is visible.
Okay, cool. Okay, should we start?
Yes, go ahead. You can
Okay,
start.
okay. So today's session is mostly about thinking, and we want to learn how to think in this ML space. And that's what this talk is about. It's not about very specific things about RAG. Uh, I'm mostly focusing on products and high-level design principles, which can help you to go back and study on your own and probably solve problems when you encounter them on your own, right? Because there will be new problems which you face every time you solve a new problem. Anyways, so today's talk is about RAG, which is Retrieval Augmented Generation. And the thing about RAG is that this R in RAG is actually a reasonably big part in RAG. After that, it's not much, right? Like you call an API, give a prompt with some context, it generates something. But all this complexity in RAG is coming from retrieval part of RAG, and that's what we'll try to focus on, and we'll try to look at a more traditional style of products and see if we can borrow something from there and see if there is some similarity between advertising and, let's say, RAG, or search and RAG. So there should be a lot of similarity. That's my claim. So that's what this talk is about. Okay, so today's goal is basically we want to learn how to think, and a couple of things I want to focus on today. The first thing is we want to appreciate the complexity of real world products, especially large scale retrieval systems like search, advertising, e-commerce advertising. Everything in the background is kind of the same, and that's what I've spent my lot of time on, like unifying my mind in a way that everything looks the same to me. Uh, and my claim is if you focus on retrieval only, it will be so insightful that you'll feel like there's nothing new in that except for the LLM.
Madam,
Uh, if you can mute yourself, whoever is
Yeah,
okay.
yeah, I'm muted.
So and then in the end, we'll kind of have a glimpse of uh, the philosophy of agents and uh, how we can kind of think about the ideal world, right? Like just 5-10 minutes, but that's the idea. Okay. So, anyways, this talk is about what and why and not how. And I've always focused on long-term learning. So we want to learn how to solve problems in terms of design. Okay. So before I get started, I just wanted to show like just a fun demo with what you can do with Gemini. So I'll just share my notebook for a moment, and then we'll start with RAG. Uh, yeah. Can you see my notebook?
Yes, we
yes,
can
yes.
demo for
Oh,
talk.
yeah. Okay. So okay, maybe we'll just directly start with Gemini. So the good thing about Gemini is that there's not much you need to do. You just provide a prompt and it responds, right? For example, in this, I'm just write a poetry for a beautiful sunshine, and it writes me a beautiful poetry, right? Of course, I cannot read all the outputs because these are short talk, but you can read a couple of lines and you can see that it's able to write a beautiful sunshine poetry related to beautiful sunshine. Similarly, uh,
So, Jabeza.
you could also ask uh, the question, what is the average weather in Mountain View in the middle of May? And of course, this is not purely like LLM only. It might uh, having certain kinds of retrieval tools which is able to get the right information so that it can present the right information to you. For example, if you want to know the weather of Mountain View, it needs that information, and it's very specific. Then it also needs the date, right? So, anyways, if you give this prompt, and by the way, Gemini is so good that you just have to supply contents. For example, I've just concatenated the question and the prompt. and this contents I can pass on to the generate contents method, and it does its job. And you can see the results. It says that okay, the prompt is about outfit suggestions, right? So if you just look at the output, it will tell you some suggestions on the daytime, for the evening, and things like that, right? So this is all simple, but it can do more. For example, you can just pass in a PDF. This PDF is around 70-80 pages long, and you can ask it a very specific question. For example, this is a paper for Gemini. So you're just asking how many tokens can the model process, and it looks at the document. This is a research paper. It's able to answer, right? Like at least 10 million tokens it can handle. So you can process PDFs. Again, the same thing. You just pass in the PDF file and the prompt again. So nothing is changing. It's reasonably simple to use. You can also do document summarization and things like that. For example, you can say you're a professional document summarization specialist. Please summarize the given document. And it kind of does it for you. There's a short summary. This is a repetition, I think. Now it also handles other kinds of content. For example, these are two images of two types of glasses. And then you can give a prompt like, I have an oval face. Given my face shape, which glasses would be more suitable? Explain how you reach this decision. Provide your recommendation based on my face shape. And please give an explanation for each. And it's kind of, it may be right or wrong, but it's doing a decent job, right? For example, it's saying that for the oval shape, both of these glasses could work well for different reasons. It's trying to justifying which one will suit you and why. And ultimately, it will recommend you something, right? So you can see that it's able to process a prompt along with some images together to give you the right response. Again, if you have a video, for example, here's a kind of a short video, 30 seconds. There's not much happening in the video. It's just some edge of the ocean with a lighthouse or something, I think. Not sure. So it can kind of, again, the same thing. You can have a prompt in the video again. And you can ask it, what is shown in this video? Where should I go to see it? What are the top 5 places in the world that look like this? And again, you can see that it's saying this video is kind of showing you Antalya, which is a harbor in Turkey. And then it tells you the top 5 places where you can visit, which will give you a feel of this kind of scenery, right? Again, audio understanding, you can give it an audio, ask a couple of questions. Again, the same thing. Basically, you can feed in anything and it kind of handles it. Okay, so this is just a summarization of the video, audio, and it kind of gives you chapters in the audio. And then you can also ask it to transcribe the audio with speaker, timestamp, caption, and stuff like that. And it does it for you. You have timestamp and stuff like that, right? So again, it can do transcription also. Yeah, this one is slightly more complicated. For example, again, this is a video of Google Pixel. And basically, in this video, there's a frame which is around, I think, 48 seconds. I'll show it to you. Yeah. Right. So you can see that around 48, 49 seconds, you get this image. So again, you can feed in, you can feed in the video file and that image, and you can give it a prompt. For example, you can ask it a couple of, so first thing is again contents. You can pass in video, images, prompt again together. It will handle it basically, because whenever you read data, you also provide a type of data. So it knows where to route your information and things like that because of this type of data. Okay, so again, if you prompt, you say that look through each frame in the video carefully and answer the questions. Only base your answer strictly on what information is available in the video attached. Do not make up any information that is not part of the video, and do not be too verbose, be straightforward and stuff. And the questions are, when is the moment when the image is happening in the video? Provide a timestamp, right? This is a reasonably complex question that it has to go through the video and find this image. The next one is, what is the context of at the moment when this image has happened, and what is the narrator saying in that moment? So you can see, first thing is it is able to answer 48 seconds, which is the timestamp of this thing. 1 second plus minus, but it's able to do the job, right? And then it also gives you kind of a context that in that moment what is happening, what is the description which is being said by the narrator, like the summary of that. So it's a reasonably complex thing, and again, take it with a grain of salt because these examples are from Gemini team itself. So, but yeah, still at least it works, right? Okay, the next one is the last one, and it's the most complex one. So it's an application of e-commerce. So basically, the way in which the user will use it is the user will kind of upload the photo of their living room, and along with that, maybe the user has couple of artworks, which also they can supply to the LLM. They can ask reasonably complex questions. For example, they might ask which of these art pieces is suited to this living room, and can you rank them and explain why you ranked them in that way? And it does that. You can also ask what kind of furniture will be suitable for this room, which is independent of these art pieces. It's an independent question, and it will again answer something which is reasonable. So let's see that. Again, the same thing. If you want to just describe the room, you can give the prompt and the room image. The prompt is describe this room, and it does, right? And it has described the room in a reasonably good way. Again, I won't read it all because we don't have that much time, but it's able to describe the room in a very aesthetic way, like an interior designer would want to describe it. The next prompt is basically recommend a new piece of furniture for this room, explain the reason in detail, and it says that a bookshelf would be a good furniture to add to the room, and it kind of justifies why it's saying so and all that stuff. And in the end, the last one is the most complicated example where we are supplying these 4 artwork, the room image, and the prompt. The prompt is basically you are an interior designer. For each piece of the wall art, explain whether it would be appropriate for the style of the room. Rank each piece according to how well it would be compatible to the room. And then again, you create this content, which is like a sequence of strings and images and prompts. And then again, the same thing, 1 line code, generate content, and it kind of does the job. It will sort it in a certain way. It says that art number 2 is the best fit. Second best is art number 1. Art number 2 is the best fit. Art number 1 is the second best, and see the room. It kind of makes sense. And then it also kind of describes it really well, why this is most suitable. For example, let's read one of them. This piece perfectly embodies the room's aesthetic. The minimal line work, botanical theme, and neural color palette blend seamlessly with the existing furniture and color scheme and stuff like that. So the point is that at least in an ideal case, it's able to handle reasonably complex things. So this was just a fun demo just to show the capabilities of the services we have today. I just want to, yeah. Can you see my slides?
Yes, we can see a slide.
Yeah. Now, going back to language model, in its most native form, what does it do? It kind of takes a prompt That prompt is fed into an LLM, it gives a response. And that's all, right? In the bigger context, that's what is happening. Of course, there could be a lot of complexity inside LLMs and all that stuff, but that's the most simple way to look at it. Now, there's a simple code where I'm taking 1 billion llama model, and I'm asking who is the CEO of Google and why he became the CEO of Google. And this I've done after Sundar Pichai has become the CEO. And very confidently, this model says Larry Page. First thing is, no details. It doesn't really answer the question why he became the CEO. Second is the answer itself is outright wrong, right? And then I take the 8 billion model for Llama and ask the same question. It's able to say it's Sundar Pichai, and it describes why he became and stuff like that. So, first thing is that two different models are behaving in different ways. Either because of capacity, that 1 billion parameters, it's not able to have enough inherent knowledge in it to answer the question. That's one possibility. Or the training data itself didn't have that information, which is not the case because the whole LLM thing started after 2021 or 2022. And Sundar Pichai has been the CEO for a long time. So we cannot assume that the information was not available. We can assume that the capacity was not enough. But either ways, the problem is that we cannot trust just based on the weights, right? And there's not much code here. That's why I'm not going to the notebook. It's like a couple of lines, so I'm not going. I've just copied the different snippets, what model I'm using and stuff like that. Okay, someone has a question. Go ahead.
Yeah, I have a question. So you are using two different models for these two prompt?
Yes,
I mean,
yes. So
why
you
there
can
is
you can
okay.
see the model, right? This is 8 billion model Llama 3.
Yeah, so
And
this one is generating a long response, and for the other one,
this is a 1 billion
where
Llama.
okay, okay, okay,
So it's a smaller model. That's the only difference.
okay.
Any other questions? Okay. So basically, the problem is that we cannot trust LLMs to have all kinds of information in the weights itself, right? It will struggle either if it doesn't have enough capacity, or it will struggle if the information itself was not available during training, right? And we cannot train these big models all the time, right? It's not, it's very costly. And that's where augmenting a retrieval system to what we were already doing comes in, where if I can augment relevant information to the prompt, then LLM will have all the information it needs to answer the question, right? So that's the main idea. Yeah. Now, and basically the idea is that if I could add a retrieval system to the previous architecture, so LLM is this brain and it was receiving some prompt and it was generating some response. That was the old version, which is in this corner. Now, instead of directly feeding in the prompt, what we do is we kind of use a retriever which takes in the query or the prompt. It looks at its own database and it sees if something is relevant to the query. And if it finds that if something is relevant, it will add that extra information to the query. And it could be just like a concatenation, right? You just add information after the query. You create this long string with that context. You pass it to the LLM, and LLM will generate that response, which is kind of slightly biased towards that additional retrieved information which you just added as context. So that's what RAG is in the most simplistic way, but we will very soon enough see that RAG can be very, very complex. Any questions here, what we are trying to do?
Hi, Devendra.
So, and by the way, I'm not able to look at the chat because I'm looking at my presentation. So please feel free to raise your hand and ask a question. Yeah, go
Hello.
ahead.
Yeah. Sorry, it's a basic question, but in the RAG, whenever you study the concept, we see that we have a vector database where, based on your prompt, based on embeddings, similar content gets fetched, added to the database, then basically you get the answer, right? But then the examples or demo you just showed seems to be very straightforward, wherein you just put in the PDF with the content along with the prompt, and you get the answer to it, right? So how is that different from at least the theoretical things that we learn, or is it a very easy implementation?
Basically, it's an 80-page PDF. You could say it's very small because it's not millions of documents or millions of snippets. So search will become easier when you have lesser amount of content to search through. And the whole challenge of search comes in when you have a bigger corpus to search from, then you start making mistakes. That's the challenging part of having accurate retrieval. Otherwise, yeah, I mean, I agree. Like if you have just one PDF, it's a reasonably easy task. Implementation wise, it may not be that straightforward, but in terms of ideas, it's a simple task. It's one PDF.
And because it's Gemini, which has most larger context windows, it's possible, is it? Or
Yeah, I mean, all providers have very large context windows. Like now, I think now it has crossed 100,000. But yeah, it's a reasonably large context window. So of course, I mean, if you have a larger context window, you could supply a lot of information which LLMs can process. But there are papers which kind of says that uh, after a certain level of context size, the performance starts to degrade. Uh, but yeah, that's another argument. But yeah, still 30,000 is the number which they're reporting, which uh, is kind of a good number, where the performance keeps on increasing up to context length of 30-40,000. Beyond that, it starts to degrade or something. There's some reporting of that kind. But yeah, I mean, the bigger the context window, the bigger the information the LLMs can get, right? And it doesn't have to like focus too much on the weights of the model.
thank you.
Hey Devendra, Anupam here. So I have a quick question. I mean, how do you make a decision that, I mean, in the previous example, you're looking for the CEO of a Google, right? So you
Yeah.
use a different model to come, I mean, get the right answer versus, I mean, so I should change my model to something which has a
No,
higher
no, no.
capacity.
I was just demonstrating that it could give a wrong answer. I'm not changing model
But
in
okay,
my product.
can I use the 1 billion model with RAG and get a correct answer?
Possibly, but I will, given my experience, I feel like at least you should have 3 billion if possible.
Okay.
But yeah, I mean, I feel like it should work with RAG, but still to be in a comfortable space, like have at least 3 billion model.
So I'm just asking, how do
Yeah.
you make that judgment call? That, I mean,
You evaluate, right? You see if
okay,
it works or not.
okay, okay.
There's no prejudgment. I never pre-assume anything. I don't even decide beforehand. For example, let's say I'm working on a problem, and let's say the product guy wants to have an agentic product, but I will not force myself to be agentic in my solution. I will look at the problem and I'll think about what should be the solution. It may or may not use LLMs. So similarly, here also I will not pre-decide what I should use. But there's also some constraints of the business. For example, if you are evaluating LLMs in real time or something, if you don't have enough capacity in terms of hardware, these are the limitation which forces you. There will be some upper limit of number of parameters you can handle because of the cost. But beyond that upper limit, you cannot pre-decide what you should use. You have to always test it out. But if you are in the open source domain, choose any good open source models. And in the beginning, maybe you have to evaluate on your task and see which ones are significantly better. But once you are at the good enough level, you don't have to worry too much about it.
Hi,
Because,
Devendra. Just one
yeah.
small question. You mentioned that the, because it's retrieving the text, if it's a large amount of documents, it can be hard for the LLM to make a good call because it's now appending all this data with your query. At what point do we go for a different, or rather, which other technique is good when you have a large amount of data sources? Like which technique will be a good approach?
So we'll
You
talk
drop
about
down.
it, but that is more related to the retriever. That retriever can be very complex to handle very large amount of data. And we will going to we'll look at it like in a couple of slides. Anything else? Okay. So let's move on. So basically, I'll just show you a couple of products and try to show you how complex they are. And eventually we'll kind of reach RAG and then we'll see some patterns. So that's the idea. So here are a couple of examples. There's a Netflix example where it's a reasonably large retrieval system of very high complexity. There are like many models which kind of works together to give you that experience. Similarly, in search also, it feels like you just give it a keyword and it shows you the results, but internet has billions of documents, and that scale is very hard to handle. And in real time, like this shows you like results in fraction of a second, and you cannot like go through billions of documents and find the relevant stuff, right? So there's a certain pattern which people have come up with over the last couple of decades, and that is now a standard pattern which almost every retrieval system uses. For example, just to show you this result, there may be let's say 15 models or something which are working together to show you this result, right? And we'll discuss that in a moment, but I'm just trying to show you how complicated things could be. Similarly, Perplexity recently added this shopping tab where you can chat with Perplexity and it will show you some products and you can go to the product page and purchase. For example, let's take this homepage of Netflix. Again, it has many retrieval systems inside it. Can you guys just make a guess how many machine learning models you could imagine, which you can see here at a very basic level?
More than 10.
Okay.
I guess you mentioned 15.
No, that was for search, but
Okay.
yeah, it could be here also. Yeah, I mean, it's not a bad answer, 10 or something. Totally possible. Because there are very small things which makes up this homepage, right? For example, a model will be there to decide what should be in the banner because this is the biggest real estate on the screen. So they will work really hard to have a very reasonably good model to have a choice of what should be here. Then this 97% match based on your preferences is, let's say, another model. This description might come from a model. What they show you in each of these rows can come from a model. So this itself is, each of these things I said is a pipeline, and that pipeline will have 5-6 models, each of them. So you multiply these numbers with that 5 or 6, right? So 1, 2, 3, 4 into 5, 20. Similarly, even in one row, there could be more than one model. Okay. So we'll discuss that in a moment, but even in a single row, there is a possibility that there's more than one model. And I'm not talking about the pipeline. Like there could be two pipelines in this one row. Similarly, again, Netflix is personalizing at a very granular level. For example, let's say it has decided that Stranger Things should be the recommendation. It will even run a model to decide which artwork to show you so that you might click on the play button and engage with the content. So there's this work on personalized artwork, which kind of uses like a bandit or something. But yeah, this one is not a complicated model, but what I'm trying to say is that these small things, for every small thing, they have a model, right? Similarly, let's say the recommendation system has decided that Goodwill Hunting is the movie you want to recommend. Again, there could be like a user with romantic preferences based on the historical views. There could be another user with comedy preferences based on historical views. And these two users, so the model has pre-decided now that Goodwill Hunting is the recommendation. Even beyond that, they will decide that which user should see which poster so that they are more likely to click on it. Right? For example, if you have a romantic preference, this image is more suitable for this movie versus if you have a comedy preference, maybe you are a Robin Williams fan and you would prefer this kind of a poster in terms of engagement, right? So for every granular thing, there's a model, right? And that's the complexity of a real product. Yeah. So again, simple question: how many models do you see? And this time you have to justify why do you see so many models? But yeah. I cannot see the chats, by the way. Please unmute yourself and speak.
At least 5.
Why do you come up with that number?
So basically, one is for like monitoring the trending charts. So I think maybe there may be a pipeline to see at least which region you are from, which local, based on your neighborhood proximity or the location where you are, what is more popular in your region. And basically then the critically acclaimed TV dramas, maybe they may be fetching from the journalists or the critics that have been rated in my region. And lastly, the top picks, I might have been using say the top list from say from a Reddit post, or I have searched it here. And also maybe there may be each model to see the real estate or the order to decide which should come first, and also the image which might capture my profile. So I think that's what I could come up with.
Yeah. So all of them are good arguments. And yes, like if you want to show the trend, you need a model to know the trend. It could be a very simplistic model also. Like it doesn't matter what the model is, but you need something to order these things. Here also it could be even human curation. There may or may not be a model. And then again, there could be some algorithm which is giving you this. And for each of these, again, they might be selecting a certain image for a certain profile. It may not be like user level. It might be demographics or region, whatever, right? So first thing is, for every movie, there's not an independent model, but there's a model which kind of decides for each movie, which you can run offline and pre-compute and stuff. But yeah, but if I look at it at a very simplistic level, 3 pipelines are here to show you 3 rows. That's a very simplistic assumption, even if I ignore the images as images and stuff. But what I am saying is that even at that simplistic level, there might be 2 pipelines in each row. Why? First thing is value of real estate. You have a screen. The top of the screen is more valuable and the left side of the screen is more valuable, right? So you want to show more valuable stuff at the top and more valuable stuff at the left side. And then there are companies who will compute pixel level efficiency. that if they show you something on some real estate, eventually they'll see if they spend some resource by showing using some amount of pixel, they'll see whether this recommendation led to some play which they can attribute to and things like that. So that is possible. So the measurement itself is very detailed in all these product companies. Second thing is, traditionally A/B testing was used to see whether the production model is better or the new one you're proposing is better. But in the traditional setup, you expose a certain amount of users, let's say 5% of users, to your new model, and 95% of the user will see the old model. But the 5% user will totally be exposed to the the new model, right? And that is kind of, first thing, it has a risk that you're totally exposing the user to your new model. Second thing is, you are only exposing it to 5% traffic, so you don't get enough data very quickly. For that, these guys, what I have done is they interleave. For example, you can see these, if I have it, okay, I don't. So you have these slots here, right? Let's say you have two models for each row. One is a production model, one is a new model. So instead of totally exposing the user with one model, what they do is, let's say production model is model number A and the new model is model number B. So they will present it to user as A, B, A, B, A, B, A, B, A, B, which means that whenever I'm labeling A, that recommendation is coming from model A. So one user will see A, B, A, B, A, B, A, B, A, B. Second user will see B, A, B, A, B, A, B, A. And that's why it's unbiased also, because every pixel is getting both models. And you can expose 100% of the user with this idea and very quickly collect data. And Netflix does this stuff. So just for that reason, each row could have at least two models interleaved. And by two model, I mean two pipelines of many models. And why I say that, we'll know in a moment, because we'll look at one pipeline, and based on that, you can assume how many models are there in one pipeline. But just think of one pipeline as having one purpose, to do something, right? So yeah, so that's about measurement and number of models which will be involved and how complex a product is. Okay, now Netflix has reached that level where they are now working on kind of personalizing the homepage itself. Like your homepage is personalized to you. It will be different for me, and it will be different for you. And that's where it has reached now. And it has, like, over, I don't know, maybe 20 years. I don't know the age of Netflix, but it has had this evolution where it started with a very simple model, which is personalized rating prediction. And then they move towards a model where they're having personalized ranking. And here you're trying to predict the rating. Here you're trying to predict an ordering of items. The prediction itself is an ordering of items. Versus now, they may not like totally implement it, but they're working towards a personalized page generation itself. Yeah. Any questions till now?
Just one question.
Go
For each row in the homepage, as you have mentioned, group one, group two, for each of these row, there is a separate ranker or what, and multiple models are feeding into that ranker. Is it?
So what I'm saying is, every model itself is a ranker, let's say. So each pipeline will generate a utility which you can use to rank, right? So now, let's say you have a production pipeline which will generate a certain utility for certain purpose, and based on that utility, you can sort the movies and show it. Let's say you change the pipeline slightly by changing one model in the pipeline, hoping that that will improve the performance of the whole pipeline. That's your model B. which will also have its own utility on which you can sort. Now you have these two, I mean, for simplicity, I'm saying these two models. Now, in a traditional sense, you would have production model A, and all these movies are coming from production model A only, right? You sort it by relevance or something, or utility. Now, what I'm saying is that a more efficient way to collect data, because model A is being used to show everything in this row. That is for user number, let's say X. For user number Y, let's say user number Y falls in that 5% of experimentation traffic. For those 5% of users, you will be exposed to the new model. And then every movie for that user will be coming from model B. But this is very inefficient in a way that only 5% traffic is being exposed to the new model. So it will de-risk because it's only 5%, but it will also reduce the amount of data you collect for measurement, because in the end, how do you measure, right? Like, let's say watch time is your metric. You want an increment in watch time, let's say 2% increment in watch time because of your deployment with statistical significance. And to achieve statistical significance, you have to, by statistical significance, I mean that you have large enough data that you're confident that your metric you have computed, you can have some confidence in that metric, right? Because it could be just noise because of the small amount of data, right? So then if you just expose your model, expose the user with just 5% of new model traffic, you would need a longer time duration to collect a lot of data so that you become confident whether that new model is better or not. Versus if I expose it to 100% traffic, but with an interleaved idea, you will collect that data 20x faster, right? If it was taking 20 days, you will collect that same amount of data in 1 day.
Right, right. Got it. But just a follow-up question here. As far as what I know is that you talked about Model A and Model B, right? So both Model A and Model B will generate their own movie recommendations, right? And then
Correct.
there will be a third model, which is the ranking model, which will take the output of both of these and then rank them 1, 2, 3, 4, 5, and so on, right?
Okay, so that is what I was calling utility. It may not be ranking model, it could be a weighted combination of multiple things, including the value of the real estate. So it depends. But what I'm trying to say is that, let's say what you're calling a ranker is a utility number for every movie. So one pipeline is giving you one utility, right? So model A, when I'm saying model A, it's pipeline A. When I'm saying model B, it's pipeline B, which will give you utility A and utility B, on which you can sort movies, by the way.
Understood, understood.
Yeah.
Thank you.
And if I can see some 15 chats in there, but I'm not reading them. So you have to speak. I cannot read chats. Okay.
Yeah, hi,
So yeah,
hi, Devinder. I have one more question.
yeah.
So, for this pipeline to work, so in case of large scale data, right? So
Mhm.
in that case, we as an engineer, we need to, means we need to segregate data and feed into the model in such a way that this model should perform in a better way, right?
Yes.
Okay. Because means not the same data has to be consumed by each and every model. The data has to be segregated, otherwise there is no point, right?
So it will depend on the task of the model. For example, if you want to just choose an image for this series, uh, the data which the model needs is very different than what a ranker needs.
Right.
So this is the training part. Even while inference, you cannot go through all the, let's say if you're in search, you cannot go through billion documents to say that what is relevant and stuff. So you have to have a certain structure, which I will talk about today. Uh, yeah, I'll talk about it.
Okay. Okay.
Okay, so we have seen like an example of a recommendation system here, and we saw like at product level how complex it could be. Next one is this search? Yeah, it's that, right? So second part is search advertising. It's even more complex than search in terms of one pipeline, because in search multiple parties are involved. Sorry, in advertising multiple parties are involved. In search, it's just user and the platform, right? But in advertising, there's a third guy who is an advertiser, so it becomes more complicated. But if you have a unified view in terms of utility, everything is the same. Either it is the same or it is a subset of it. So this is another example of search system which is very complex. Again, I'll show you in a moment what one pipeline looks like. I'm just showing you examples right now. Again here, you have ads, and also the UI also changes, by the way. All this needs a lot of engineering, right? Because if you search for, let's say, a cricket match which is happening live, it has to detect the query that it is based on certain event which is happening. And based on that detection, it will change the UI that the cricket score comes at the top, which is a special widget which has been added to the UI. Similarly, advertising also, because advertising is not organic, right? Like it consumes a real estate. So unless you make money out of it, that in a non-deterministic way, but if you're unless you are making money out of it, it's not worth showing the ad, right? And then this part also might be an ad. So you're taking so much real estate, so you better be sure that you are making some value out of it. You will not show an ad all the time, right? So a model triggers something in the real-time pipeline which changes the UI and it consumes certain recommendations to show here, right? So it's a lot of engineering. Again, I'm an ML guy, so I cannot talk about all aspects of engineering, but it's very complex. Okay, shopping I've already talked about. This is an example where, okay, so this was best reviewed celebrity fragrances 2024. And you can see that Perplexity is able to give you an answer and it shows you some products. By the way, this is a single page. I'm scrolling down, so I get the right hand side. And then you can click on some of them and you can visit the site and purchase. So this Perplexity shopping, and why I'm showing you so many examples is each one of them has the same pipeline in the background, right? And I can even predict the future. Maybe actually they announced it recently, but just by looking at this product, I knew on day one that sponsored products will be the next thing which will come to Perplexity when they want to make money or monetize this real estate. It was obvious if you know the patterns, right? Okay, so the thing is, each one of these products I was talking about has this retrieval funnel where you are searching through things, right? And when you search, you have this whole universe of tens of millions of items. And sometimes it's not possible to evaluate all of them in real time. So there's this multi-stage recommendation system design pattern in a way, which is very common everywhere. So initially what you do is you quickly go from very high number to a reasonably manageable number in couple of steps. So there are these stages called matching, pre-ranking, ranking, re-ranking. It also has other names you'll see in the next slide, but the point is at every stage, the search space reduces drastically, at least order of magnitude or couple of order of magnitude in the first step. And after that drastic reduction, you can focus on the quality of results till you get only 10 recommendations, because when you search for an item, you just need couple of, let's say 100 items you just need, right? So once you have 100 items ranked, you are done. But in real time, you cannot run a very complicated model on 10 million items. It cannot be done in real time. So we have to first use very simple models in the beginning to reduce the amount of data we have to go through. And at the middle or at the end, we can use more complicated models where we can, in real time, compute the quality of those items which has reached up to this stage. So initial stage is focused on rejection. I mean, every stage is focused on rejection, but it's like a funnel where you're going from a very high number of items to very low number of items. And before I take questions, I'll just go through one slide. This is an example of a multi-stage advertising system, and I'm showing you the life of a request. So let's say we are looking at search advertising. So you feed in the query, and for that query, you have to go through, let's say if it's Google, you have to go through billions of pages to show you the search results, which is, let's say, top 5 pages or something, because not really a lot of people cross 5 pages. So anyways, first is the selection stage where you go from, let's say, okay, the numbers here is not for Google, let's say for some reasonable mid-sized company. So you go from 10 million to 10,000 after first stage. Then you reach the relevance stage where you go from, let's say, 10,000 to 1,000. And then in advertising, basically, there are multiple parties. So each party has its own interest. For example, the user cares about relevance. The advertiser cares about click-through rate. And then advertiser also brings in some money. So there's some constraints. And that's why we have pricing and auction. Now the point is, this pipeline is reasonably complicated. In the selection stage itself, you have like three, four models or something. In relevance stage, you have 2-3 models. In click stage, prediction stage, you might have 1-2 models. Auction is just one model, but it's very simple one. But the theory is very complex. But the point is 4 here, let's say 3 here, and then let's say 2 here. So 5 and 4, 9. And if I assume this is also a model, 10. So 10 models in this pipeline. So basically, we have different focus for each of these stages. The first stage focuses on preserving what could be relevant. It's allowed to make as many mistakes as possible, but the goal is to preserve the relevant stuff in the first stage. In the second stage, the goal is, okay, so what I'm trying to say here is that let's say you have 1,000 relevant items for the particular query. I want to capture as many of those 1,000 as possible in the first stage, which let's say we call it a recall maximization stage or something. Then you have a relevance stage where the whole focus is on the results, search results, where you really want the top results to be the best. So basically, this stage is more about, if you say something is relevant, it better be relevant, right? So that's the stage, and let's call this a high precision stage. By the way, whatever I'm saying in English, in the background, it's that is the meaning of that thing. For example, when I'm saying that if I have 1,000 relevant items, I want to capture as many of those 1,000 as possible. That's the definition of recall. When I'm saying something is relevant, it better be relevant. It really means is that I'm trying to optimize precision. Then advertiser really cares about his purchases, and there's a statistical correlation between clicks and purchase. So having a click-through rate prediction model makes sense, and this relevance model and click prediction model kind of feeds into the utility function here. And this utility has many components. One is relevance, one is click prediction. There's also value of real estate, whether you should show an ad at all or not. Those components are also there, but eventually it's just like added sum of all these scores. How to tune is a very complicated topic, but basically you are just trying to find a utility function on which you can sort your items. It's just a score. And the score is composed of relevance and clicks, let's say. right? So this is an example of a standard pipeline, and everything I have shown you in terms of products, each of these pipeline will be a subset of what I'm showing you in this slide. For example, if it's not advertising, there's no need of auction and pricing, but other things are needed. Okay, I have this one slide which is hidden, but for example, there's the DoorDash. There's a blog from DoorDash, and you see that there's not much here. That there's a recall component, there's a precision component, and that's it. So what I'm trying to say is that everything is a subset of this pipeline in today's world, like every large scale system. Now, whatever I've shown you, it's the same thing, but it's a product. So there's something called NVIDIA Merlin. It's an open source kind of a software for building recommendation system. So they have done a high quality software engineering on your behalf. You have to just fill in the missing pieces for your task. Again, for every kind of these things I'm discussing, there will obviously be training because you need a model at every stage. So this bottom red box is based for training, and the top box is basically for online inference, which is a real-time system. And what is really happening is that it takes in a request, it gives you a response. Right? For example, it takes in a query, it gives you some results. And if you look at all these stages, although the names are different maybe, but you'll see that the things we have discussed, except for the auction in advertising, it is there. For example, the first stage is called the retrieval stage in this software, which is basically the selection stage where you are going from 10 million items to some couple of thousand items. And usually your vector databases, search, BM25, bag of words, all these are ways to kind of retrieve relevant documents. This will come in this retrieval stage. The next stage could be either some invalid data, or there could be some business logic, like let's say you are trying to advertise some illegal stuff. So maybe there's some other model not in this pipeline which is flagging that this is illegal stuff. So it will just filter it out at this stage. And then this scoring is basically the relevance module in the previous slide. So it has a scoring model, which is kind of a relevance model, which gives you top K candidates or something. There could be some business logic for whatever reason you want to remove or resort it in a certain way. So that's what NVIDIA Merlin can give you out of the box. Excuse me. Now to power retrieval, right? You have to kind of match query with documents. So for that, you have to train the models. So for example, you might need an embedding model on which you might do like nearest neighbor search, right? Or any of the modern vector database companies you can use, whatever. So the point, okay, in this case, you don't have to use those because NVIDIA will provide it, I think. So the first stage is basically you have to train your embeddings so that when you give it a query, it can retrieve the top documents, and tuning the embeddings for your task is your job. What should be the loss function is up to you and stuff like that. The whole machine learning thing, right? But once you have your model and your nearest neighbor, you can actually retrieve the top K candidates. And this stage is really fast. And you can go from 10 million to 1,000 really quickly. Then you have some logic to remove certain things. Then you have this scoring thing. Again, you need to have this training pipeline for relevance model, which you will do it independently, right? So basically, this is the pattern, and people have built softwares on top of it. And again, the whole argument is every product I've shown you follows this pipeline. Okay, so now the question is, why are we studying all this stuff? Because including whatever products I showed you, plus RAG also follows this pattern. I'll show you an example of a complicated RAG, and the ads pipeline I showed you, my claim is that's the future of Perplexity, because they will add sponsored ads sooner or later, right? Okay, so now let's come back to, and example of an advanced RAG. So yeah, yeah. So basically, in the middle, you can see the RAG pipeline, which shows you these stages, and you'll see some kind of correlation of that pipeline to this pipeline. For example, you feed in the question. The first stage is query translation. And what query translation is doing is that it is reformulating your question in various ways. It is breaking down the question into smaller components. It's going back at a higher level. It's rephrasing it. It's adding some hypothetical documents to it. So whatever it's doing, it's kind of reformulating the question in various ways. And when you feed in this new query, you have a much better context to search. And you can do these things in parallel as an OR logic that with each of these, you get some documents. You have a union of all those documents, which goes into the next stage. And in this OR setup, by definition, it's a high recall optimizing step where we are trying to capture as many relevant documents as possible. It's okay to make a lot of mistakes here because the goal of this stage is to have a high recall system. And while I go through this stage, when I say high recall system, that's also your eval metric, right? Now it's up to you how much resources you have to evaluate it. That's up to you. You can hire humans. You can have some machine do it, some big LLM do it, whatever. But the point is, at least you know the metric you want to target. So query translation in the retrieval system also, the whole goal was to increase the recall, that you don't want to miss the relevant stuff in the first stage. It's okay to make a lot of mistakes. The second part is routing. Again, based on the prompt, maybe you have to write, you have to use some path. This can be done even with an if-else statement. For example, if I show you this, okay, maybe this one. So some model, do I have it? Okay. So anyways, let's take this example. So when I search something, I'm showing an ad here, right? And for the UI to change, first thing it has to decide that this query has a purchase intent. If the purchase intent is triggered, then the UI will change and this ad is being shown, right? So that if-else statement with a model is happening here also, right? That first stage query reformulation is happening here also. We are just not able to see in the product, but in the background it is happening. Let's go back to the RAG again. So the first stage is query translation. High recall is the goal. Second is routing. Even in the advertising example, there was routing. So till now, there's nothing new in RAG. It is just the type of nature of routing is more complex because an LLM is kind of choosing it. But we could have done that stuff there also. It was just that LLMs didn't exist when these things were designed. But based on the routing, different paths will be taken. And for each path, you need basically a collection of things which you can focus on. By the way, here we are just having this query translation. We have not retrieved it yet. The goal is to have a high recall. It has not happened yet. It will happen here when you actually retrieve it, right? But collectively, the initial stage is focused on high recall. Okay, so once you have your reformulated queries in various ways, you can kind of use these databases to retrieve a collection of documents which are relevant, hopefully, but relevant in a way which is high recall, not in high precision way. So till this stage, I hope you can see my mouse. Yeah. So at this stage, where you see these documents, the whole goal was to have a metric that these documents, when I evaluate it, it should have a high recall for my question. So it's okay to have a lot of shitty documents in here, which is not relevant. But the goal is to have those documents here, which is needed, which has the answer. So first stage is that. Then the next stage here is basically the retrieval stage, where now the goal becomes high precision. That whatever document crosses this, it better be relevant. Till here, we are just making sure that we don't miss any relevant stuff. It's okay to make a lot of mistakes. But after this funnel, this retrieval stage or ranking stage, we have to put in all the energy to make sure that whatever passes through this funnel, it better be relevant. That's the design goal. Whether you achieve it or not, it's up to you, experimentation, all that stuff. And again, there are other ways. For example, now RAG has been evolved in a certain way that it has access to browser. So if it doesn't find enough relevant stuff, it can also browse the internet. Anyways, the point is once you have your relevant 20 documents or 50 documents, you can feed in that context along with your question to your LLM, which can generate your final result, right? And if you think about it, this is actually a subset of, again, that pipeline I just showed you, right? It just doesn't have auction and pricing. Post-processing, it could have, but it depends on the version of RAG you're using. But at least I hope I have convinced you that the same design principles is working for all the products I've shown you. It also works for RAG. I'll take questions now. And I
Yeah.
know this diagram is very complicated,
Yeah.
but at least this middle part you can see and just get the gist of that pipeline which I just showed you. Of course, this has a lot of details which Ajay might talk about in other sessions. But this middle part having these stages, and this is a simplistic stage, is what is really the topic of discussion today. It's not really RAG in a sense, but RAG is also using the same principles. Someone was asking a question, I think. Yeah, go ahead, Arun.
Yeah, so my question is, so when we come from the funnel, first we are looking for a relevance, high relevance sort of a mindset, and then when it is up to the retrieval side or the re-ranking side, re-ranking side, we go for the precision side. Is there a scenario or is there an application where it's the other way around, where say for example for a medical use case, we want to be highly precise, and also if it is not there, we just have to say there is no relevant, or that a sort of a negative way that I don't know sort of a scenario. Is that like what can be that model design?
Correct. So basically, there are two kinds of search engines. One is precision based, like Google. Second is, let's say, a specifically designed search engine just for medical records, or let's say legal search engine, right? So let's say if you are a lawyer researching for your case, what you really want is, it's okay to have some mistakes in the first page, but in the first 10 pages, I better have all the relevant stuff, right? You cannot, it's debatable, but I feel like you cannot achieve both. You basically, because if you achieve both, you have a perfect system. And if it was possible, search guys would also be using it. So I don't think it is possible to achieve precision and recall simultaneously. I mean, very high precision and very high recall simultaneously, there's a trade-off. But if you know what is the goal, for example, in Google search, the goal is that the first page should have what I want. One of them, not all of them. Versus in a case of a lawyer, he wants that he will click on the next page, next page, next page. But in the first 10 pages, he hopes that all the relevant cases for the query is there. That is his design goal. And for that, obviously, we will not have the precision funnel. We might have another. If you are good at machine learning, there are loss functions which directly optimizes recall and precision, right? Or precision at k, recall at k. You have loss functions to directly optimize them. But the point is, if you know your goal, you will choose your loss functions in this funnel in a certain way so that you get the job done. There could be also some tuning. For example, you might have a re-ranker for relevance, for precision. You could also have another ranker for recall. You could have a weighted combination, and you can tune the weights so that you can adjust and balance out precision and recall. That again, coming back to that final utility function on which you sort your documents, right? So yeah, I mean, you have to understand what you need, and based on that, you have to train your model in your way.
Right. Thank you.
Any questions?
Thank you for the session, Devendra. Like one quick question is, for a multimodal RAG, which could be the good options to start experimenting? Any suggestions?
See, the thing is, in the end, everything is an embedding, right? So somehow, if you can have like a shared space where photos and text both can reside, then to a nearest neighbor's point of view, there's no difference in image and search, no difference in image and text. Right? It's just an embedding of the same size on which nearest neighbor will operate, or your vector store will operate. Now, but you will also have some metadata with all these embeddings. So let's say somehow, if you want to have an input as an image, so you'll have that extra metadata that it's an image if it's relevant to your use case. But in the end, it's embeddings. And once you have embeddings, you find the nearest neighbor documents, whether it be image, whether it be text, and you can feed these images and text to your LLM. For example, there are now vision language models, which can take in images also to generate more text out of it. So your LLM could be like a vision language model or some kind of multimodal language model. In terms of the document database, from nearest neighbor point of view, it's just an embedding, right? And once you have that embedding to find your nearest neighbor documents, and once you have that metadata that this is an image, you can feed in that image to your LLM in a way that it's an image, right? Embedding was just there to search, but once you have your collection of documents again, you can reconsider it, how you can present that to the LLM.
Okay, yeah, sure. Thank you.
And by the way, some of the answers I'm giving is just coming from me. They may or may not use it that way, but I'll give a logical answer. Even if no one is doing it, it will work. Because I'm not like seriously following everything happening in the field, because my coverage is much broader. But I'll give a logical answer and it should work. Go ahead. Someone is raising a hand.
Yeah, Devendra, so when you just mentioned about the image embedding, how is it gonna be or worse in both the cases? Like you have an image, embedding the image directly versus extracting the text and then retrieving it. What difference, or is it depending on the application, or is there any gain if we directly embed the image rather than extracting the text and I would say build a RAG on top?
So first thing is the simplicity of implementation. It matters. So again, my point of view, but if it matters that you should have like a simplistic implementation, then converting the image to the description of the image and then feeding in the text as the document itself will have a very simplistic implementation, right? Versus if you directly feed in the image into a vision language model or something, or some kind of vision model, at the least, the implementation will be more complex. Now it is subject to evaluation that if you are such a specialized product that the performance on the images is very, very important, then you will consider both cases and see what is better. And usually, there will be some information lost in translation. That's my belief, obviously. But you have to empirically check which is better. But usually, information is lost in translation. So, image to text, whenever you do, the text cannot describe everything in the image. What if what is relevant to your application is totally missed by that translation? Because let's say there's a car in the image in front of a building or something. But what if the query is about the color of the skies or something, right? And maybe the LLM naturally doesn't adapt to that part, or the translation model you're using, the caption generation or something, whatever. You're basically translating image to text. What if the relevant information is lost in translation, right? So it depends. It's very empirical. But yeah, I mean, if you want a simple implementation, you first convert to text and use it as a text document. Go ahead, Ankit.
Yeah, hi Devendra. Am I audible?
Yeah.
So, I was just asking on question on the recommendation, like, how does sponsored traffic comes into picture for any cold recommendation? By cold recommendation, I mean like where the user demographic is quite new to the sample space. So we know like for organic traffic, we know like using the users demographic, there are some certain business metrics that we use for creating the recommendations. But how about the sponsored traffic gets, I mean, captured over there, given an unknown users search query?
So if you're talking about sponsored traffic in terms of content, let's say take Netflix example. Even if there's a new movie, which is the cold start problem for the new movie, that movie will have its own description of the movie. You can also get that description from IMDb page. And that description can be matched with other description of other movies. From there, you can borrow the feedback of other movies. That's one possible solution for the cold start of movie, right? So the description of the movie itself can be matched to description of the nearest movie or couple of nearest movie, and based on the now you can expand, right? Once you know about relation to the old movie which has a lot of data, then your possibilities of solution will expand.
Got you. So essentially, we have to start with the movie name itself, maybe the genre of the movie.
You need some kind of side information to get into the feedback rich data.
Okay, got it.
There's also a feedback collection mechanism. For example, for the cold start problem, it's also possible to randomize that this is a new movie. It doesn't have enough data. So even independent of relevance, I'll push it randomly once in a while and collect feedback. And till I don't have a good relevance model, I will keep collecting feedback. That's also another possible solution to cold start. Any one of them you can try based on the risk of the product and other things. But the first version of the solution is very less risky.
Got it. So, I mean, it will follow the same architecture of the organic ranking itself, just that the number of KPIs will be low over there while doing the ranking.
It depends. Because, yeah, I mean, you can follow it actually. No, it's the other way around, right? For example, let's say ranking is happening for a user profile or demographics, right? The only question is whether this new movie will be in the ranking list or not, right?
Yeah.
So it is the same pipeline, but the movie is not part of the list. So how can you introduce that movie to the list? So I feel like it needs a special treatment. For example, let's say that the recommendation system is giving me an old movie, and that old movie is the nearest neighbor of this new movie in terms of metadata. If that is possible, then I can just replace that movie with this new movie because it's the nearest neighbor in metadata.
Okay.
So it might need special treatment. It depends.
Got you. Okay.
Yeah. Okay. So maybe we'll okay, go ahead.
Yeah, just a last question. Can you give us like small example for query translation? Like what exactly do we end up adding to the user's input such that our LLM is better suited for answering the query?
So one example in search is synonyms, or let's say there's a search term which is very ambiguous. So you might want to add some details to the search query, and that search query is happening enough number of times that it is worth that effort to have that metadata for that search query, which in this case is called hide. But there we are actually not hypothetical in nature. We are actually having real content. Another example is that let's say you have a very, very high level question. Maybe it has multiple sub questions inside it. So you might want to decompose that bigger context question into smaller questions, which might help you get more documents. Or if you have a very low level question, maybe going to a higher level abstraction in question might help you. For example, let's say you have a query of a very specific brain disease. Maybe going one level above in abstraction might get you more documents in terms of recall, and we will hope that the high precision stage handles it after that.
And to do this query translation, right, all of these high decomposition, are we training LLM specifically for these tasks?
No. Basically, you can prompt it and it will do it for you. For example, this diagram has been taken from LangChain itself. So they have this tutorial on RAG where they actually show you the prompts, how you can achieve these things.
Okay, understood. So we are just kind of concatenating the other prompts based on their tutorials, right? To get this.
Yeah, I mean, it's a design principle. For example, once you do it, once you have many versions of the question, what do you do with it? One is you can pass in each of the questions to this pipeline and get some document, keep doing the union of all the documents. Or you could combine them in a certain way together and get documents. There are two options. I would prefer the or one, like you pass in each of the version independently and do a union of documents because the goal is high recall by design principle. So I would have preferred that, but I don't know what other people are doing. And then we hope that after we have a high recall setup in terms of whatever documents we have collected, the high precision will filter out the irrelevant ones. And for each of these things, by the way, it's just an idea. For example, if the question is not long enough or good enough, basically rephrasing it in a certain way or augmenting it with certain kind of information adds a lot of text to the question, which through correlations with the document, there could be higher chances of matching, right? And that's what hide is. Decomposition is basically breaking a higher level question into smaller questions. So once you know the idea, you can prompt the LLM in a certain way that it will try to do it. And off the shelf LLMs can also do it because RAG usually doesn't involve a lot of training. Almost never, I think, because if you do train, it's called raft. It's not RAG anymore. But anyways, the point is, once you know the intuition, you can prompt it in a certain way for RAG application. But the same ideas, by the way, have been used in search 10, 15 years back also. So without RAG also it's possible. They will try to do synonyms. They will try to rephrase the query. Although LLMs will do a much better job of rephrasing, they will add some kind of document. They attach real documents, not hypothetical documents. But these things people have tried in past for search also. So once you know the goal, you can struggle to make it work, right? Because it will always be a struggle to make something work, right? That's the part of the job.
Right, understood.
And Mridul, if I may add, right, in our Discord channel in week 2, one of the links that says all RAG techniques, okay, that's probably a nice, simplest way to see some of these implementations, right? Like hide or prompt expansion or re-ranking or all those things. Right? So there are like short examples that are there in that repo. So probably that will give you more intuition from this diagram.
Okay, I didn't notice it. I'll check it out.
Yeah,
Thanks.
the top of week 2 channel, you'll see a bunch of links given there.
Okay.
And regarding the data, I'm pretty sure Ajay is covering all of them or most of them. So you should not worry too much. The idea of today was the design principle.
Yeah.
And the details is always relatively easy to figure out. Debugging is the thing which is harder. And these small hints I'm giving you, for example, here you have to test the recall. So even if you, let's say, hire some human annotators to judge the quality of your retrieval, I have given you a hint that you have to check the recall or recall at K or something. Here also you have to judge the precision. So these are the small hints which will allow you to understand what is the problem with your system. Because end result is not how you fix things. You need to know the problem before you fix something. This is not true just for LLMs and RAG. It is true for all parts of machine learning. Yeah. So just for the sake of time, I'll quickly finish it and then take questions. I'll take 10 more minutes, I guess. So in RAG, basically you have categories of query. For example, implicit facts, explicit facts, interpretable rationals, and hidden rationals. It's very weird in terms of name, but if you take examples, it's easy to understand. For example, explicit facts. And by the way, each of these has levels, right? Levels of complexity, L1, L2, L3, and L4, which will make sense in the next slide. Why are these levels? It's easy to hard. Now, if I take explicit facts, just take an example. In which country is UEFA Euro 2024 being held? To answer this question, you have a data dependency, a segment containing a sentence, blah, 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 right? This is explicit facts example. Another example is implicit facts, where let's say the query is, what is the capital value of the company Elon Musk found in 1999? So it's also a factual query, but it's asking something which is indirect. And the data dependency is that first you have to understand what Elon Musk founded in 1999, which was X.com. Then it was rebranded to PayPal, and then you need to know PayPal's current capital value. Right. So this is an example of implicit fact. The third category is interpretable rationales. Again, it's not interpretable, the name itself. So we take an example. So query is, do I qualify to apply for a 5-year Japanese tourist visa in Shanghai? Again, it has certain data dependency. It requires information on multiple entry visa requirements from the Japanese consulate, etc. And then the last one is hidden rationales. For example, let's say the query is, how will the economic situation affect the company's future development? Now, the data dependency here is a collection of financial reports with economic and financial rationales required. So from top to bottom, the complexity of query is going up, right? So based on this classification from L1 to L4, this survey paper has come up with this categorization that if you have level 1, 2, which is facts, for explicit facts, you can use a RAG. For implicit facts, which was the second example, you could use one of these. And then for rationals, you can use these things. And for hidden rationals, you can use these things. So again, the goal is not to focus on how. The goal is to focus on categorizing the queries in a certain way in order to have some kind of mental map of when it's difficult and when it's not. Now there's this whole thing of agentic RAG. I will not cover any of it, but I just wanted to end with what is the dream, right? So so there's something called a chain in terms of implementation or in lang chain, where if you look at a RAG, right, it's a sequence of steps. This is a sequence of steps. Whatever be the prompt, it will do the same sequence of steps again and again. It doesn't matter what the prompt is. The RAG will do the same thing in this form, which I'm showing you, right? But again, you can show that there's this RAG and all that stuff. But let's assume it's a simple form, the one which I discussed, not the diagram, right? So whatever be the input, it will do the same sequence of n steps. And that's called a chain. It's hard coded in the code itself that this is the sequence of step I have to do for this application. And that's kind of a medium level RAG, non-agentic RAG, let's call it, right? Now, the good thing about chain is that it's reliable because every time it does the same thing. Every time. But what is the dream, right? In agentic things, let's say I have an agent, I tell it, I wish I wanted to travel to Japan, right? And can you help me plan my travel? So it has to get all the information of all the tourist spots in Japan, all the relevant cities, how will I travel internationally, how will I travel domestically, book my tickets. So there's a sequence of things it has to do, right? Now, imagine a world where all these small tasks is like an API call, where to book tickets, it's an API call, to figure out the routes, there's an API call, to do domestic travel, there's an API call. So there's this all possible small things. You have a certain API, which I'm calling step 1 to n here. So there's this universe of n steps which is possible in the world, and LLM is the one which will decide which steps are relevant for the query and in what order, right? So that's an example of an agentic system with very high autonomy, that it is also deciding what to do and in what order. But once you are reaching there, you'll see that for every input, because the LLM is choosing one of, not one, a few of these steps, and in what order, every input will have a different execution order, right? And the LLM itself deciding what to do and then eventually executing is kind of the dream state for an agent. And there could be simple things, there could be complicated things. But the main discussion here is in agentic systems, there could be simple stuff, there could be complicated stuff. In simple stuff, the LLM is just deciding whether you have to do something or something else. For example, in advertising example, whether to show an ad or not show an ad, right? So it's this simplistic setup is called a router, where you are choosing to do one or the other, which is the least level of control an agent could have, versus a full autonomous system where the agent is deciding what to do and in what order. And the whole point is basically the flexibility of the agent and the reliability is inversely proportional. And once you have reached here, uh, so yeah, basically you are not getting this autonomy at no cost. You are risking reliability to get that autonomy. So people who are dreaming of very high reliable systems with insanely autonomous systems basically are actually accepting a risk of lower reliability, which is fine in a way, but you need to know it. You cannot be in an illusion. Okay, so that's all about it. This slide is not relevant. I'll take questions.
I think a lot of questions you have already answered. So
Yeah. Anyways, we're also like, I'm pretty sure I'm beyond my time. I didn't even know how much time I had to spend, but yeah, happy to take questions. If there are no questions, that's also fine.
all right, if there are no questions, we can